Hello everyone, today we're going to go over the origins of the law of conservation of momentum in quantum mechanics. Now, to put a TLDR on this video, continuous space translational symmetries yield the global momentum conservation law. That's what this entire video is about. If you guys did not understand what I just said, don't worry, you're in a safe boat here. We are going to cover every single bit of that. So let's begin. So in classical mechanics, we say that momentum is conserved if the rate of change of momentum equals 0. Okay, the rate of change of momentum is 0. Now, usually in high school, we just say, oh, momentum is conserved, but we don't answer why in like high school physics. It's just say, okay, momentum is conserved, and from that assumption derive all of these other principles. But it turns out that in classical mechanics, we can actually prove when momentum is conserved and why momentum is conserved. That's something that we can prove, and we prove this by studying the Lagrangian, and we find that continuous transformations of space translations of the Lagrangian yields a conserved quantity, that being the partial derivative of the Lagrangian with respect to one coordinate, and we define that as momentum, and then we say, oh, momentum is conserved. That's the reason in quantum mechanics. In quantum mechanics, we do something a bit different. We instead use Hamiltonian formalism, and with that we can prove that momentum is conserved with the Hamiltonian. Now, to be a bit more specific, to be a bit more precise, in quantum mechanics, we no longer speak of the energy of a system. Instead, in quantum mechanics, we talk about the expectation value of the momentum of the system. And if that equals 0, we say that the expectation value of the momentum is conserved. That's what we really mean when we say energy is conserved in quantum mechanics. Okay? So, in this video, we are going to prove why this is true in quantum mechanics, where this comes from. And we're going to talk about cases where this is not true. So, let's begin, actually. Let's really begin. So, let's define the transition operator. So we define the transition operator, the space translational operator, as the operator where it acts on psi of x and it outputs psi of x minus some number a. This corresponds to shifting the wave function to the right by some amount. So we're shifting the wave function to the right by some amount. And this might seem a bit non-intuitive to you guys. Shouldn't the wave function shift to the left? You're subtracting x by a. Well, this actually corresponds to moving to the right, and it makes more sense if you guys actually plug in the values. So psi of x minus a is actually shifting it to the right by a, and we can actually graph this. Just say this is like psi of x, and then this over here, the dotted line, to represent psi of x minus a. And then a is the amount that it's shifted towards the right. And now we say psi of x minus a, we call that psi prime, and that's going to equal the transitional operator acting on psi of x. So this operator acting on psi is just shifting it to the right by some amount. That's what it means. Hope you guys can understand that. So what is the actual value of this operator? Well, to find that, we have to expand psi of x minus a in a Taylor series. So doing a Taylor series expansion, we have this. It equals 0, infinity, 1 minus n factorial, minus a to the n, second derivative dxn psi of x. This is psi of x minus a in the Taylor series expansion. Okay, so now what we're going to do is we're going to assume, let's assume that the derivative d over dx can be written as I omega hat over h bar, where omega is some operator we have yet to specify. So doing that gives us that this series expansion is equal to 1 over n factorial times minus ia over h bar omega to the n psi of x. This is because since the derivative is I omega over h bar, we just apply that here, and then you'd have I over h bar omega to the n, so that's the derivative here. Then we have minus a to the n. You stick that in here to get this expression. Okay, so not that hard to follow. And now we notice that 1 over n factorial, the series from n equals 0 to infinity of 1 over n factorial, that's just Euler's number, right? So we have an exponential here. And we have, so this is just e to the minus I a over h bar omega times psi of x. Because we have an exponential here. So it's e raised to this, then multiplied by psi of x. Okay, so now what? Well, now we can cancel out both sides. We can cancel both sides by psi of x, and we now have, this implies that t hat of a just equals e to the minus I over h bar omega. And that's the formula for the space translation operator. Now, we've yet to actually specify what this omega is. We can find out what omega is from the derivative. So d over dx is I omega over h bar. So doing some clever manipulation, just basic algebra, multiply both sides by h bar, then divide by I, we obtain that omega equals h bar over I d over dx, which equals minus I h bar d over dx. Okay? Now, so really, we just assume that d over dx could be written in terms of omega, and then we rearrange terms to find that omega equals minus I h bar d over dx. Now, we may jump and say, oh, look at that. That's the momentum operator. We just found out that omega hat equals the momentum operator. This would actually not be quite correct. It should actually be the other way around. We actually define the momentum operator as the operator that generates these space translations. So it's not that we just take you just find that momentum is this operator. No, instead we define momentum as this operator. We define the momentum as the operator that generates these space translational symmetries. And then we define the observable corresponding to that operator as the momentum. So that's what momentum actually means in quantum mechanics. And it's analogous to what it means in classical mechanics. Okay. So we can just relabel omega, or really we're just defining p hat as omega hat. So t hat of a equals e to the minus I over h bar p hat. Okay? So now that we know what it means to translate a function, what does it mean to translate an operator? What does it mean to translate an operator? So, this is going to be a bit non-intuitive, but when we say, when we talk about translating an operator, we say that we have q hat prime. So q hat prime means the translated version of the q hat operator. And we define the translation of this operator as this. So psi prime q hat psi prime is psi q hat prime psi. So what do I mean by this? So what I'm saying is that we define the translated operator as taking the inner product of translated wave functions, and now that's just equals to the inner product of the untranslated wave functions, the original wave functions, but our q hat is changed by some amount to make this equal to each other, and the changed value is said to be the translated version of q hat by definition. Okay. And from this, we can actually derive the formula for the translated version of q hat. And so, psi q hat, psi prime, that equals psi times the translation operator, right? Then times q hat times the translation operator psi. We can actually move these operators to the front since they are unitary. You can prove that yourself that the translation operator is unitary, but we're just going to assume it for this video. But you guys can prove it yourself. So we move those to the front to have, so we have psi t hat dagger q hat t hat and then psi. Okay, it's t hat dagger since t hat was in the covector, so moving it out yields a dagger there. Okay, and this equals psi q hat prime psi from our definition earlier, and this means that q hat is this. We just derived that q hat prime is transition operator dagger q hat times the transition operator again. So that's the formula for translating an operator. Now let's actually apply this formula to the momentum operator. Okay, let's apply it to the momentum operator. And flip this page around. Okay. So the momentum operator, translated, is just going to be t hat dagger momentum operator t hat dagger. Sorry, just normal t hat. So to make this calculation easier, we were going to plug in a test function psi that we can later on cancel out. So t hat dagger x hat t hat psi of x. That gives us t hat dagger x hat. Now t hat operating on psi of x is just psi of x minus a by definition. So now we have t hat. Oh, also, yeah, we can just keep on going here. We have t hat dagger. The precision operator times psi of x minus a. That's just x times psi of x minus a. So now you have this operator, this inverse operator, since the adjoint of a unitary operator is inverse by definition, and we have this inverse operator acting on this entire thing. So we can treat this as like one big function. We could call it phi if we want to, and if this operator is acting on this function phi, like this phi of x function, what we do is we change it to phi of x plus a, since it's the inverse, right? So instead of phi of x minus a, it's phi of x plus a. So if this is acting on this entire thing, what we do here is we change our x's to x plus a, since it's the inverse. We have x plus a times psi of x minus a plus a. These a's cancel out, and now we have psi. Sorry, now we have x plus a times psi of x. We can then cancel out our a's, sorry, our psi of x, our psi of x's. And then we have that x hat prime equals x prime, which equals x plus a. And this is a really kind of obvious result, because it's also a very beautiful result, because we have just found out that our that how we define the transition operator on x hat, it captures our notion of what it means to translate an operator. Because x plus a, that what does x plus a means? what does it mean? So x plus a just means that we are shifting our coordinate system, the coordinate system itself, we are shifting it to the left by some amount a. This is a really cool result. Now, I really want to emphasize this because, say I have a coordinate system, I'd have psi of x, right? Then here it would be psi of x prime, right? So operating on the position operator, it actually corresponds to instead moving your actual coordinate system backwards by some amount a, so that it appears that your new function was shifted to the right by some amount. So it's equivalent to say that, instead of translating your function to the right by some amount, you're instead shifting your coordinate system backwards by some amount a. So if we shift this coordinate system back by some amount a, our function here, psi of x, now looks to be translated to the right relative to that point, relative to the person on the origin. It kind of ties into relativity about how if you change your coordinate system, things look shifted to the left or to the right by some amount, but in this case it's to the right. This is a really cool result that we've obtained here. So what does it mean to translate the momentum operator? So we just do the exact same thing. Okay, just do the same old thing. So we have operator, it's prime, that's just t hat dagger p hat t hat. We can instead then just put a test function psi of x. I have t hat dagger p hat t psi of x. Okay, so now we expand this d hat times minus I h bar d over dx of t hat psi of x, that's just psi of x minus a. And now we have t hat dagger acting on all of this. So what we do, again like before, we just treat this as a new function and change the x to x plus a. So this gives us minus I h bar d over dx times psi of x minus a plus a. The a's cancel out, and you get minus I h bar d over dx psi of x. You don't change this x in the differential because it's not an x, it's d over dx, right? And notice that this is actually the same thing that we started with, right? Well, sorry, we notice that this is actually the momentum operator, right? Well, we cancel out the psi of x's, right? And we can find that the momentum operator, the translated momentum operator, is just the momentum operator, right? Because minus IH bar d over dx is the momentum operator as we found out before. This is also really cool since, and it kind of makes sense, right? Since the momentum, we defined it, the operator, to be the generator of these space translations. So it makes sense that when the momentum operator is translated, we get the same thing, since it's the thing that generates the translations. So b hat prime is the exact same thing as p hat. So now we are going to prove a general statement. We are going to prove that q hat prime of x hat p hat equals q hat of x hat plus a p hat. Now this where q hat is a general operator, okay? And this probably already seems a bit obvious to you guys, but let's actually prove it in the general case to make sure that our intuition is correct. In quantum mechanics, oftentimes it's not. So how can we prove this? So to prove this, we have to assume just one thing. We are going to assume that our operator can be written as a power series. That's what we're going to assume. Our operator can be written in terms of a power series. So what will that power series actually be? Well, let me just find part of my notes. Where is it? Okay. Sorry for the delay here. Okay, so we want to prove the q hat prime of x hat p hat, that's q hat of x hat plus a p hat. Sorry for the bit of a day. I just have to get some of my notes because we don't memorize every single thing here, right? So we assume that it can be written in terms of a power series. That power series being m equals 0 to infinity, n equals 0 to infinity, a mn x hat to the m p hat to the n. So that's the power series. Okay, so trivially, q hat of x hat plus a p hat is just going to be the same series, m equals 0 to infinity, n equals 0 to infinity, a mn, and then x to the m plus a p hat to the n. Okay? So we have to prove that the translated version of this is just going to equal this expression over here. Okay? So let's start. So we have t hat dagger q hat of x hat p hat t hat test function psi of x. So it's the same thing as last time, but now instead we have to expand q hat of x hat p hat in terms of this power series. So m equals 0 to infinity, n equals 0 to infinity, a mn x hat m p hat to the n t hat psi of x. Okay, probably see where I'm going with this. This is just t hat dagger m equals 0 to infinity, n equals 0 to infinity, a mn x hat to the m p hat to the n, and then this operator is just psi of x when I say. And I want to point something out real quick. So you guys may be wondering why we're explaining it in this series. Well, remember that a general operator can be written as a combination of the position and momentum operators. So what we're doing here is we're just saying, okay, we have a general operator and we're just writing it in terms of x hat and p hat. That's what we're doing here, because we can do that with the general operator. In case you don't want to take my word for it, you can just read any intro to QM textbook. Like in the first chapter, they probably just highlight that a general operator can be written in terms of momentum and position. That's the same thing in the classical mechanics. Pretty much like almost all variables can be written in terms of the position and the momentum. So let's get back on track. Okay, so you have this now, this here. So you have T dagger operating on all of this. This is acting like a big old function, really. And now you actually have to write out p hat to the n in x hat m. So we have, let's just do this straight upwards. We have t hat dagger, let's see, m equals 0 to infinity, n equals 0 to infinity, a m n, x hat to the m, that's just x, p hat to the n, that's minus I h bar d over dx, the definition to the n, and they have psi of x minus a. Okay? And now we see this as one big function called, you can call it psi of like x hat, p hat if you want to, but sorry, phi of that. So we should have this big function, and we just like before, we just change our x's to x plus a's. Yeah, that's what we do. And we actually change our momentum operator as well, but there's no x in the momentum operator, so m equals 0 to infinity, n equals 0 to infinity. I'm getting a bit lazy with my m's and n's. X, that's just x plus a. This operator remains unchanged since there's no x in it. So we get minus I h bar d, sorry, this should be to the m, by the way. Can't forget that. This is 1 over dx to the n psi of x plus a minus a. The a's go away. This equals series m equals 0 to infinity, n equals 0 to infinity, a m n. This is just the momentum operator, right? So you have x plus a to the m, p hat to the n, psi of x, but we can just cross cancel our psi of x, and this is q hat of x hat p hat. Okay? And if you pay close attention, this is literally just equal to this, right? This is just q hat of x plus a, p, and that's the same thing that we have here, which implies that q hat of x hat plus a, p hat equals q hat translated. Sorry, I'm just really tired. This is like my third take. This video. I need to sleep right now, but I'm crazy doing physics, right? So here is the operator, and we've just proved. Okay, so what's next? So now, what's next on the agenda? We are going to show, we are going to comment on the symmetry of the Hamiltonian. Cool. Okay. So, let's define a couple of things. We say that the Hamiltonian, h hat, has a symmetry, or a system is symmetrical. Pretty much, h hat has a symmetry. Okay, has a symmetry if the translated Hamiltonian is the same as our original Hamiltonian. That's what we mean by symmetry in physics. Translated Hamiltonian is the same as our original Hamiltonian. Okay. Now, our Hamiltonian from quantum mechanics, remember, that's p hat squared over 2m plus v of x for one-dimensional, one-particle system. So what will our translated Hamiltonian be? Well, this is actually why I just proved the last thing. Because now we don't have to go through operating the translational operator on our system. Instead, we can just change our x's to x plus a and leave our momentum dormant because we just proved that we can do that. So this is p hat squared over 2m plus v of x plus a. Okay. So if it's symmetrical, it means that this equals this, right? So it means that p hat squared over 2m plus v of x equals p hat squared over 2m plus v of x plus a, trivially implying that v of x equals v of x plus a. Okay, this is the good part. So if v of x equals v of x plus a, where is it constant, that means that the Hamiltonian is symmetrical. There's a symmetry. The Hamiltonian is symmetrical, meaning that translated Hamiltonian is our OG original Hamiltonian. Okay. So we call this a continuous translational symmetry. So you have a continuous translational symmetry if v of x equals v of x plus a, right? If v of x equals v of x plus a for all x. So if for all x, if for all x, v of x equals v of x plus a, we have a continuous translational symmetry. This trivially corresponds to having a potential that's dormant. That doesn't change. Because if it doesn't change, then the potential at x and the potential at x plus a will be precisely the same. So we have a continuous translational symmetry. That just means that our potential, we move it a bit, it's the same, and that implies that the Hamiltonian is symmetrical. Okay. Now we have a discrete translational symmetry. That just means 30 minutes. Wow. That v of x, oops, gotta move this up a tad bit. That v of x equals v of x plus a for some x. This is what this symbol I mean for some x. Okay. So this corresponds to having a periodic potential. So it may go up, then go down, then go up, then go down, then go up, and so on. Maybe just terminates there. And if you have, here's x here, right? For some a, x is the same, but not for all a. Like, only for some x is x plus a the same. Like, if I move x over here, well, the potential is different. But if I move it by the period, I have the same thing. If this is true for only some x, then our potential, we see there's the discrete translational symmetry. Since I mean, for this translation, the Hamiltonian will be the same, but not for the in-betweens. Okay. All right. So with these two words, we can finally show what the entire idea of this video is about. I'm going to introduce it a bit more subtly. Is that a word? Subtly? A bit more subtle. Okay, so let's do this. Okay. So, I'm going to restate what I said above. H hat has a symmetry. H hat has a, well, I guess, a symmetry if H hat prime equals H hat. We know, this is our first big idea. Let's get some of those big ideas. Our second big idea is that H hat, or that a continuous transitional symmetry, which means v of x equals v of x plus a for all a. I think there's an ant crawling on me right now. Sorry, guys. Wasn't that great? There's a bunch of ants crawling on my legs right now. That is terrifying. Sorry. Alright. If I get an allergy from this, that really sucks. For all a, that implies that the Hamiltonian is the same and that's for a translational symmetry. So it's a like we have a symmetry if our Hamiltonian is the same, but under which operation is it the same? Well, it's a translational symmetry, and we get that symmetry if you have a continuous translational symmetry of the potential. All right. Okay. And from this, we can show an amazing, spectacular result. Okay, so let's clear our heads and actually do this. I hope I don't have to do this like a fourth time. So I'm trying to get my mind straight. Because there's a bunch of ants on my leg right now. Okay, so H hat prime, that's just T hat dagger H hat T hat. Okay, and that equals H hat. So we can multiply both sides by T hat, right? If you multiply both, so let's just take this, right? So here, let me just take another space. So you have T hat dagger, H hat T hat equals h hat, right? You multiply both sides by t hat on the left. These cancel out since it's unitary. So we have the h hat t hat equals t hat h hat. So h hat t hat equals t hat h hat. This implies that the operators to commute, the commutator of h hat t hat equals 0. Okay? Okay, so it is 0. Nice. Okay. And I'm going to read this a tad bit up. A bit. Okay, so let's reintroduce our operator here. So remember that this operator, t hat is just e to the minus ia over h bar p hat, right? So now that's a t of a, right? That's time translating an observable by a to the right, okay, or to the left depending on the observable. Okay, now let's change a. Instead, let's make it an infinitesimal translation. So, of course, if you have a continuous symmetry, right, it's symmetrical all throughout. That's the case. If these commutes, we have a continuous symmetry. That means that moving it an infinitesimal away from the original point will also this commutator will also be 0 trivially, right? But here, from I move it an infinitesimal amount to the right or to the left. Sorry, this is a bad example. Here, if I move it an infinitesimal amount, I still got the same potential, right? So why are we doing this? Why am I talking about the infinitesimal? Like, it makes sense that the commutator should still be 0 for an infinitesimal translation. But why are you even talking about this in the first place? Well, it's because what we're about to prove is going to be much easier to work with an infinitesimal translation. Now, you can't prove this for a non-infinitesimal translation, but it's going to be much more simpler if you use the infinitesimal translation. I'm bet you pure right now. Okay, so for the infinitesimal translation, that means so that just equals e to the minus I infinitesimal over h bar p hat. Okay. Do what next? Okay, so that's the infinitesimal translation, and this is going to be approximately equal to 1 minus I infinitesimal over h bar p hat. We have to technically rigorously define what this infinitesimal is. You guys can think of it as 1 over n, as where n approaches is getting closer to infinity. That's the kind of vague sense of what the infinitesimal is. You can define more rigorously in real analysis, but let's just keep it simple. So this is approximately equal to this, right? So the commutator of the Hamiltonian in this time transitional operator, the infinitesimal one, should commute, right? Because we have a continuous transitional symmetry of the entire potential, so it should still commute. Okay, and this is just the operator of approximately 1 minus I, the infinitesimal, or just del h bar p hat. Okay, and what does this equal? Well, this is just the Hamiltonian times 1 minus I infinitesimal over h bar p hat. I believe it's plus or minus. I think it should be minus. Yeah, minus. Hope you guys could see that. Minus 1 minus I infinitesimal over h bar p hat times the Hamiltonian. Okay, and this just equals this is just h bar minus I h bar del over h bar p hat plus so not plus, minus h bar minus I, same thing, I h bar p hat. Okay, so this is what it is. All right. Now this implies, so like this is a constant, right? This is a constant. This is a constant, and this is a constant. When I'm applying this entire thing, and these all commute, right? Like this should be 0, right? So if these commute, well, I have h bar p hat, right? And I have, oops, I should have to put this here. So if h bar, it's not h, right? The Hamiltonian, the momentum operator here, and here I have the Hamiltonian, the momentum operator again, and this equals 0. All of this combined together, it gives me 0. Okay. Oops, I also forgot to. Yeah. So here's the Hamiltonian. Here's, I'm thinking, sorry for repeating myself, but I want to make this clear. Here's the Hamiltonian. Here's p hat. And then here's p hat. Here's the Hamiltonian. And if this whole thing equals 0, and everything else is a constant, except for this Hamiltonian here, but like it's at the same placement. But these aren't, right? This is h bar p hat. Here's p hat h bar. Everything else is the same, and that's 0. That implies that h bar p hat equals p hat h bar, and implies that h bar and p hat, the Hamiltonian and the momentum operator commute. This is amazing. If you don't see how it's amazing, you don't understand what I just said. That may be my bad, but this is a phenomenal result, because we've just shown that if we have a if you have a continuous symmetry, if you have a continuous transitional symmetry, which means that h bar equals h bar prime equals h bar, which is caused by v of x equals v of x plus a, that we found that through all this algebra and math, that implies that h bar p hat equals 0. Okay, h bar p hat equals 0. Okay. Ran out of paper, so ignore this person over here. So we have just shown that if v of x equals v of x plus a for all a, that's a continuous. Well, really, it's not a continuous symmetry. Sorry, it's a continuous translation, right? And this implies that the Hamiltonian translated equals the Hamiltonian. That's the symmetry. Well, I guess you could really call it either one of these, the translational symmetry. But this is, if this symmetry is induced by this is said to be a continuous translational symmetry. Okay. And from this, we just found out that it means that the Hamiltonian, the momentum operator, commute. Okay. Now you guys can be like, okay, yeah, that's cool, and sure, they commute. Who cares? But remember Ehrenfest's theorem. Ehrenfest's theorem is that the rate of change of the momentum of the excitation value of the momentum is equal to I over h bar times the excitation value of the commutator, right? And you find that this is 0 if you have a continuous transitional symmetry, right? So this is 0, which implies that the momentum, the expression value of momentum, is conserved. Amazing. Mind blown. Wow. Clap for yourselves. Like, this is amazing. It may just be me, but I think it's not, because we've just shown that we just shown the nature. Like, one can just say, oh, if the Hamiltonian and operator commutes, well, then we have conservation of expression value of momentum. We've got to step further and say, okay, well, that's caused by a continuous translational symmetry of the Hamiltonian, which is then induced by v of x being equal to v of x plus a for all a. because the potential is symmetric under a translational operator, so is the Hamiltonian. The Hamiltonian has a translational symmetry. We call that a continuous translational symmetry. Like you can say that the potential has the continuous translational symmetry. Kind of goes both ways, but usually we say that the Hamiltonian has a continuous translational symmetry, and that implies a conservation law, the conservation of the expectation value of momentum. This is an amazing result. So yeah, that's how. That I hope this statement that a continuous, also we call this a global conservation law, because it means that the momentum, the expectation value of the momentum, is conserved for all x, right? For all x. If the potential has a discrete symmetry, that implies that the Hamiltonian has a discrete symmetry, which implies that this is only a local conservation law for some x. Okay. So I hope you guys understand the statement that a continuous space translational symmetry implies a global momentum conservation law. If you guys need any more clarification of that, please tell me in the comments. But because we just, love physics, we have to do one more proof, one more problem, then we're done. So let us prove, I really need more paper. I gotta find, but yeah, I need to find more paper. So let's prove one more result. We're going to kind of generalize this to multiple dimensions, well, 2 dimensions here. Let's prove. So what is it again? That if a Hamiltonian, so the Hamiltonian for 2 particles with some interacting potential, that's going to be equal to minus h bar squared over 2m partial x minus h bar squared over 2m partial x plus the potential v of x1 minus x2. Okay, so we are going to prove that this sorry, we're not done yet. Saying what we're exactly going to prove. You have to apply it. So this transition operator on psi is intuitively just going to be psi of x1 minus a. Like if you guys don't know what I'm doing here, see my video on there's another ant on my. Why are there so many ants in this room? Dude? Oh my gosh, this is actually scaring me. Okay, let's just shoot that ant away. Again, this is like actually terrifying me right now. Okay, but there's an ant on my. There's so many ants here. Sorry, I just. Okay, sorry about that. Just making me more paranoid. If you guys don't know context, I hate ants. Okay. So what were we gonna say? Okay, so yeah, if you guys don't know what I'm saying here, watch my video on n-fold degeneracy of a particle in a 3D box. Wait, no. Wait. Oh yeah, wait. No. Watch my video on the Schrodinger equation for n-body problem, because this is all in 1 dimension, right? So watch my video on Schrodinger equation. It's called Schrodinger equation n-body problem. I go over what this Hamiltonian means. Okay, well, kind of. I go for the case where v of x t v of x1 x2 is just v of x1 plus x2, but it's the same thing for in the interacting potential. The equation also separates. Yeah. So this is our context so far. Now what we're going to prove is we're going to prove that the expectation not expectation value that t hat is going to be e to the minus a over h bar big P hat, where big P hat is just P hat 1 plus P hat 2 of each particle. It seems intuitive, but let's prove it. We're also going to show or prove, so let's just prove, that the rate of change of the expectation value of momentum is 0 in this system. Because remember, a system where v of x plus a is not true for all x. This energy momentum is not conserved, by the way. That's the case where it's not conserved. So yeah, let's start. Let's prove a first. I'm going to prove this really fast because there's ants like all over my table right now, and yeah, so we're gonna prove this like really fast. So okay, first we have a t hat of a psi, we have psi of x1, x2. That equals psi of x1, psi of x1 minus a, sorry, and x2 minus a. That equals psi of x1 minus a times psi of x2 minus a, assuming the separation of variables of the wave function. This equals the summation of n equals 0 to infinity 1 over n hat minus a to the n dn over dxn psi of x1, then n equals 0 to infinity 1 over n minus 1 over a h bar p hat to the n psi of x2. So what we did here was we just expanded both terms in terms of that series, the Taylor series expansion that I talked about earlier. And this equation actually separates the two parts. With this potential, they separate with that potential. So we can separate our wave function into two parts, part them together. Okay. Now this equals n summation of n equals 0 to infinity 1 over n hat times minus I a over h bar p hat to the n psi of x1, and then times n equals 0 to infinity 1 over n hat times minus I a over h bar p hat to the n. Oops, I wrote this part for this part. Sorry, this part should just be this. Yeah, let me just do this. This should be my bad, minus a to the n derivative and then psi of x. It's basically the same thing. Okay, almost done. And then we get this, right? Hopefully you guys can see what I'm doing right now. Okay, and then we see that these are both exponentials. E to the minus I a over h bar p hat times e to the minus I over h bar p hat. This should be p1, p2, p1, p2. Psi of x1 times psi of x2. And for that psi of x1 is that. There's an ant crawling on my face right now. Goodness gracious, dude. Goodness gracious. Alright. So this is, if you can recall, this is just e minus I a over h bar b hat 1, e to minus I h bar b hat 2, psi of x1 x2. Okay. And then from this we just combine these two terms of e to the minus I over h bar, factor that out, p hat plus p hat. That's just e to minus I, p1 plus p2 actually. E to I over h bar p, where p is the sum of the individual particle operators of momenta. Okay, we've just proven that. And I have to prove that this still implies a conservation law thing. So h bar equals t hat this, okay, and this implies that the commutator is 0. Would you multiply both sides by t hat? Okay, so now we take t hat to this to be e to the minus I of big P hat over h bar, the infinitesimal translation operator, where big P hat is just the sum of the individual terms. Okay, so remember that we showed shown that can be written as that. Okay, so this is approximately equal to 1 minus 1 delta over h bar big P hat. Okay, where this can be a over n as n approaches infinity. Okay, and then what we do now is take the commutator of h hat and this operator. The commutator of this operator and h bar 1 minus I h bar p hat, and that should be equal to 0. That's equal to that's equal to h bar 1 minus, this is where the genius comes in, p hat plus p hat. That's a genius move there, because we can take this big p hat, separate that into the individual momenta, a sum of those, and then we have a commutator of h hat wad minus 1 this of small p hat, should be p1 p2, so of p1 plus the same thing but for p2, p1, here's p2. Okay, let me just see. Yeah, so we're just distributing the term inside of there. Okay, and this of course implies that h bar and then big P 0. Yeah, so actually for this part we didn't have to put these together. My bad. We don't have to put them together to show that the commutator is 0. Which is, we used to use the same argument as before. We just distribute these things in, but it implies that h bar in big P hat or h bar in p hat 1 plus p hat 2, if we just want to keep that expansion out, that's 0. Okay, so this means that hp minus p hat h Hamiltonian equals 0. This implies Hamiltonian working on p hat plus p hat minus p hat plus p hat. This should be p1, p2 equals 0, which implies that the Hamiltonian acting on p1 plus the Hamiltonian acting on p2 equals basically p hat 1 is the Hamiltonian plus p hat 2 which is the Hamiltonian. Okay, this implies that the commutator of the Hamiltonian and p hat 1 equals 0. The commutator of the Hamiltonian and p hat 2 should be 0, right? Since like these are the same thing, just swapped, we can just show that these are the same, or cross cancel these ones then and show that these ones are the same, right? And through Ehrenfest's theorem, this is my original take. Ignore all of this. Through Ehrenfest's theorem, we have that d for dt. That's just I for h bar of h bar p, and that is going to be 0, right? Since this is going to be 0 for p1 and also p2. Therefore, the derivative of each of the momenta, so this equals this, equals 0. So this equals this, and they all equal 0. Energy is conserved for the system. So yeah. We didn't even have to, actually, never mind. Yeah, so energy is conserved. Wait, yeah, we didn't have to, wait, did we or not? I think the potential by nature is, translationally, symmetrical, but I'm not sure about that. So, yeah, so we've just proven that, the conservation of the momentum operator, of the exposition of the momentum for this case, and the other cases. Yeah. Finish our proof, and yeah, hope you guys really enjoyed this video. This 1-hour video. It took me a while to make this, so please share this, guys, with your friends that also study QM or just want to know about QM or just want to know about why momentum is conserved. And if you guys love this video, share it, yeah, all that cool stuff. And yeah, have an amazing day. And that's why let me see if I get this right in the first take. Continuous transformations space transformation symmetries imply global momentum conservation laws. Bye.